Okay, so we're going to do a video today to talk about the units that are needed when considering some of the mathematical analyses of energy, and then we'll work through a couple of practice problems. So the first one first thing you should be aware of is that a lot of these units are definitely not metric. So for example, the first unit that I think is useful to know is the British thermal unit, BTU. And unlike the nice, neat calorie, a BTU is how much energy it takes to raise 1 pound, definitely not metric, of water 1 degree Fahrenheit. So this is very similar to the definition of a calorie, but that's within the metric system, and so a lot nicer numbers to work with. So this is an energy content. If you want to talk about huge quantities of energy, like the amount of energy that's being produced within the coal industry in the United States, you'd have to be talking on the order of quadrillions or 10 to the 15th BTUs, and so we will see quad come up. Gallon, you should be fairly familiar with that as a unit of volume of a liquid. The reason I mention it is that a barrel is something that we will talk about in terms of volumes of petroleum. And so a barrel of petroleum is 42 gallons. And so this will come up at times. Another thing that you may come across are short tons, or what in the United States we call a ton, which is not metric. A US ton or a short ton is 2,000 pounds, kind of along the lines of cars, right? A cubic foot is a volume that we would use for gases, and you'll often see CF as the abbreviation for that. This is cubic though, right? So if you have to do conversions to meters, cubic meters, just be very careful about that. All right, so this will talk about natural gas, how much you're burning in your heater or in a natural gas power plant. Speaking of electricity, you should also be familiar with the unit, the watt. This is technically a measure of power, and we use it when we're talking about electricity, speaking of things like how much electricity does it take to turn something on. If you don't give it enough watts, the item will not turn on. But if you want to actually use something over an extended period of time, you need to talk about the watts times the amount of time you're using this object. And so that will be a unit that will refer to the watt hour or the kilowatt hour. These are metric, whereas the others are not. So let's see how some of these are used in math problems. We want to know how much energy it would take to raise the temperature of 1,000 gallons of water by 25 degrees Fahrenheit. And in order to do that, we need to know, first of all, that a gallon of water has a certain amount of weight, because we saw that BTUs raise pounds of water in temperature, which is another thing. If this asks how much energy, the first thing that should come to your mind is that this is asking for how many BTUs. So you want to set up an equation that would give you a number of BTUs, and see if you can set that up. Pause the video and see what you get. Okay, so you know that if you want to end with BTUs, you got to make sure you have BTUs in the numerator. 1 BTU is equivalent to 1 pound of water. We've got, this is for just 1 degree Fahrenheit, so at the end we're going to multiply everything by 25. We can convert the pounds to gallons, and the gallons we get rid of because it tells us how many gallons. And so you should have gotten 208,500 BTUs, which, if we want to put that in scientific notation, 2.09 times 10 to the 5th BTUs. Yeah? All right, let's look at this kind of stuff again in a different situation. So here, we want to know that we have heating fuel. That's the kind of oil that maybe your house is heated with. and that has 133,000 kilobtus per gallon. And so now we want to know how many are in 1 barrel of heating fuel. So again, we know we're going to be looking for a certain number of BTUs. And I suggest that you pause this now and see if you can set it up and then check your work. Okay, so first step is to convert the kilobtus into scientific notation to make it easier to work with, which is 1.33 times 10 to the 5th BTUs for each gallon. And then convert 42 gallons to 1 barrel, and that gives us 1.6 times 10 to the 6th BTUs for every, that's wrong, per barrel of heating oil. It's a lot of energy. Okay, let's look at how to use these kilowatt hours and watt hours. Okay, so we have this scenario talking about something called a methane digester, which basically takes waste. In this case, we're talking about animal waste, but it's also used these days for sewage. And it produces methane from the anaerobic decomposition of organic waste. And so you can have this on a farm. This farm has 500 cows. We've got a digester that costs a certain amount. We know how much electricity is being used per year and how much that electricity costs. And then we can also learn about how much electricity can come from the waste of a single cow. So if we take a look at this, we have the number of kilowatt hours of electricity that can be produced in 1 year. So part I, how many kilowatt hours per year? Well, we've got some information about a single cow and a single day and about how many cows there are. So let's see what we can get to set that up. So we use the amount of electricity coming from 1 day from 1 cow. We can multiply that by 500 cows. And then we can also get rid of the days by converting those to years. And so then we should have the amount of kilowatt hours, which is 5.48 times 10 to the 5th kilowatt hours per year. Okay, sounds like a lot. Question 2 asks, okay, so how much money would you save in 1 year if you were doing this? So we're not going to consider how much it takes to install that. That's the next question. But basically what that's asking is how much would this be worth in dollars, right? Because we want to know about dollars per year. And we know we're making this much electricity per year, so that just needs us to take into account how much money each kilowatt hour is worth. Whoops, so we take that number from above, 5.48 times 10 to the 5th kilowatt hours per year, and convert that into $0.1 per year. Per kilowatt hour. Right? So we got rid of our kilowatt hours and we're left with dollars per year. And so if you wanted to pause it, you could, but that's a pretty easy math setup, just making sure you understood what that meant. They also specified nearest $1,000, so if you do out the math, that is $55,000 per year. Don't forget that a dollar sign is a unit, so make sure you treat it as such when you're doing your unit conversions in this. Sometimes you can go international and put the dollar sign at the end of the number like they do in Europe and elsewhere, and that sometimes can help us remember that we're looking at that as a unit. Okay, last question is asking how many years would it take to recoup the cost, right? So again, we're looking for years. That's pretty easy in terms of what the final unit should be. But how would you set that up? See if you can figure that out. Pause it and then check your work. So what I did was I used this number here. That's how much money you're saving each year. And I flipped it over because in 1 year, I'm going to save this much money, and really I want to know how long it's going to take to get there. So we're converting from 1 year, from that 55,000 into years. Here's how much money you have to make up. Basically, you could sort of interpret this by saying how many times does 55,000 go into 400,000? This is just showing you what the setup would be if you needed to think about units. You end up with something that's not a whole year, and so you should convert that into a full year. Because it takes more than 7, it's going to take you 8 years. All right, so I recommend trying out some of the problems. I have one more question for you. This is something to think about. We often have the situation where taking the BTUs found within a fuel and converting that into a form of useful energy isn't 100% efficient. And so that's something you want to definitely consider when you're looking at electricity production, for example, some of the different appliances. So how would we consider efficiency? We've got 5% efficiency, tells us that only 5% or 0.05 times whatever it is going to be used. So if we are using a 100 watt incandescent bulb for 10 hours a day, how much electricity is actually used for light production? This is kind of a two-step question. First of all, you want to remember that this really, what unit is that looking for? That's looking for watt hours. We don't need kilowatt hours at this stage, but you could convert it into kilowatt hours. We need watt hours. All right, so how much is that? When we're talking about a day, we have 100 watts times 10 hours gives us 1,000 watt hours. Yeah, but it's not 100% efficient to give us electricity. It's only 5% efficient. So what we need to do is multiply that number, 1,000 watt hours times 0.05. This is the 5% efficiency to get. So of that 1,000 watt hours, 50 watt hours are actually being used for light production, which means that the other 950 watt hours just go into heat.